Hey, welcome or welcome back. In this video we will discuss quite an important topic. I've used a bold title and somehow a clickbait title, but I quite believe that could be the final solution to the resonance behavior. So let's dive into the topic. So resonance solved, maybe. How resonance works, or else why amplitude goes infinite at resonance. The importance of mechanical reactances. Disclaimer somehow. Hey there, this is the answer I arrived to while trying to solve that mysterious behavior. I think it's the correct answer, even if it's not completely developed yet. However, it's easy to fail when decoding physics, so it's always better to remain with feet on the ground. The usual by now disclaimer regarding English, that is not my native language, so advices to improve are welcomed. So the summary: introduction, a step back, continuous motion, rectification, impedance, impedance etymology, mechanical reactances, damping coefficient, damping forces, forces and energy, forces balance, velocity sink, final recap and conclusion. So introduction. If you are already following me, you might remember I proposed the idea that before resonance, elastic force and drive are synced, while opposite beyond it. Something like this. In case you aren't, you can find link in the upper right-hand corner of the video or somewhere else. The point I came to is the following: not only on active forces we must focus, but on dissipative ones too. To explain the dynamic, I have to take a step back and show you what to me happens in cyclic phenomena, like oscillation, for example. A step back. You might already know that in resonance, one object vibrates and an identical object at rest, close to it, slowly begins to vibrate at the same frequency, the famous diapason or tuning fork common experience. What you may not know if you are quite new to the subject is that objects that work at other frequencies vibrate too when first object vibrates and emits energy. But the object that has same frequency of the forcing one, the one in resonance with it, experiences hugely greater vibrations than the others not in resonance with it. Hence, the final target of the slide is explaining why amplitude of this vibration is virtually infinite in resonance and finite outside of it. That's the picture that shows that at resonance frequency the amplitude goes infinite. Before it amplitude is finite, beyond resonant frequency it's finite and decreases as frequency increases to become even lower than amplitude at rest, weight of the mass. That is to say, starting from 0, we move and the amplitude, this is the amplitude of the vibration, increases until it becomes infinite, and then beyond resonance frequency, the amplitude of the vibration decreases even lower to become even lower of the one here at rest as frequency increases. So continuous motion. I've said in a previous video that though vibrations occur around an equilibrium point, and displacement, velocity, and acceleration pass through 0, so they stop themselves, I said that to me they are continuous phenomena. And I'll tell you why more specifically right now. Consider the image on the left. I drew the motion arc with hyphens to convey the idea. A pendulum moves continuously during its arc, not jumping micro-intermittently from a degree position to another one. Think to a quartz clock hands versus a manual winding one. In the first one, the hands jump to a position to another one. In the second, they move continuously. And I mean, in the in the quartz clock, the hands go like this. In the manual winding one, they go like this. Or at the pendulum, when the mass arrives at the extreme of the range of motion, it comes back in a continuous motion like this, and not like this. Hope this helps. Rectification. So now the conceptual forward step to do is, okay, so if it's continuous motion, then let's rectify the phenomenon. In other words, forces and velocity and displacement stop only for the intrinsic nature of the phenomenon, but not because there is something that set them back. So instead of going back and forth, we go only back, only forth, or forth. What we have then, a continuous force, that is to say, a continuous acceleration or constant acceleration, and I mean the driving force here, that constant acceleration leads to linearly increasing velocity and quadratic rise of displacement. Force is equal to constant, is equal to mass times acceleration, that is to say, acceleration is constant, so that velocity is increasing linearly with time, and space increases quadratically with time. That is one force, but if we have two of them, one opposite to each other, the global balance is zero, then acceleration is zero, velocity is constant, and displacement is linearly increasing. That is to say, F minus F equals 0 equal mass times acceleration, so that acceleration is 0, velocity is constant, and space or distance or displacement increases linearly with time. That is to say, a uniform rectilinear motion in which at each unit time displacement increases of a constant quantity, while in the previous slide displacement increased instant by a growing quantity. For example, displacement at time 1 equals 0.5, displacement at time 2 equals 2, displacement at time equal 3 is 4.5. To clarify, we are dealing with two types of motion here, uniformly accelerated motion and uniform rectilinear motion. To better understand the physics, think at a car that travels on a highway, so somehow without big obstacles. If engine imposes a torque and eventually an acceleration to the car, air and other dissipative forces impose a brake. The balance between the two is having no acceleration and constant speed. That is to say, torque and acceleration of the car, air and something else that balance themselves so that acceleration is 0 and velocity is constant. If engine exceeds dissipative forces and acceleration is felt, hence speed increases until the dissipative forces bring the balance in another point where once again acceleration is 0 and speed is constant but higher than before. And vice versa, if dissipative forces are greater than engine torque, you feel deceleration and car begins to slow down, or car speed is decreasing, of course. So if you compute displacement at time 2 minus displacement at time 1 is equal to 1.5, and so on, 2.5, 3.5. That is to say, at each time interval, displacement rises, or distance. In the other case, uniform rectilinear motion or balanced forces, it comes out that displacement at time 2 minus displacement at time 1 equals 1, and so on. At each time interval, displacement remains constant. This is the rectified motion. But if we are going back and forth in a cyclic motion, displacement becomes the amplitude of displacement. And so in one case it remains constant, In the other case, it begins to rise or grow. So impedance. Now consider this. While elastic force is balanced by inertia, what does balance drawing force? The answer is dissipation or damping, both external and internal to the system, and that's where impedance comes in. So what is impedance? It's the sum of real and imaginary damping. In one word, it's the complex damping, where complex means that has an imaginary part in it. That means that something has cyclic behavior. So let's tackle it using the substitutions I proposed in the earlier video about force oscillation theory correction. Impedance etymology, by the way, I always asked myself from the very first time I heard this strange word, more or less I was 18 years old, what the hell did it mean? Funny thing is, everyone I